Show that the matrix M is non-singular. So that means that M will have an inverse. Well, the inverse is given by 1 over the determinant of M times the adjugate matrix, which is the same as the transpose of the cofactor matrix, but it will exist provided that the determinant is non-zero. And so that's what we've got to do here. Find the determinant of M and show it's non-zero. Now, if you have a matrix A, B, C, D, and you find the determinant, which is what these lines mean, then it's just AD minus BC. So here it's going to be 4 times minus 7, minus 28, minus 10, which gives us minus 18. This is non-zero, and this implies M non-singular. Triangle R is now transformed to triangle S by this transformation, and S has 63 square units. Find the area of R. So that means we've got the area afterwards, and we want to find the area before. Now the determinant is actually the scale factor matrix. So what we're doing is we're timesing by 18 to get this area of 63. By the way, the minus, in fact, means that it changes orientation. So it might be like that. But that doesn't really come into it here. I'm just wanted to mention it. So if I want the area of R, initially we need to do 63 divided by 18. Well, that's going to be, we can just cancel out a 9 from both, 7 over 2, or 3.5. Let me show that the line y equals 2x is invariant under the transformation t. So I'm just going to sketch out y equals 2x. Now, if it is invariant under a transformation, what it means is if I have a point here, then when I transform it, it will stay on the line. It's not necessarily going to go to the same place. It's not an invariant point. It's just that the line itself is invariant. So maybe this point goes to down here, for example, and then maybe that one swaps around. I don't know. Or maybe that one goes somewhere else. You know, there's lots of possibilities. Or maybe they all just sort of move down. But we need to show that if we have y equals 2x, so when we take our matrix 4 minus 5, 2 minus 7, and we multiply it by a coordinate on this line, so it would be x and then 2x. At the end of it, we're still going to get a point on the line. So whatever we have at the top, we're going to double it down here, and then it will necessarily be an invariant line. So let's multiply this out. I'm going to get 4x when I 4x and then minus 10x, so minus 6x, and then 2x minus 14x, so minus 12x. And this, well, you can see actually the bottom one is double, so we're nearly there. I decided to say that it was x 2x, where capital X is equal to minus 6x. And that is enough to say, therefore, y equals 2x invariant under t. In the mark scheme, they actually factorize the 6 out and get it back into, oh sorry, yeah, minus 6 and get it back as this. I quite like that approach as well, to be fair, because we are showing again that we are still on the line. We're just taking whatever coordinate was and we're timesing it, the x and the y by minus 6. It will still be on the line. So there we go. That's how we deal with that part there. Well done.